Welcome, let's get cracking. So I'll tell you a bit about us. My name is Peter Menden. I'm CEO of Bright Ascension, and we are a space software company based in mainly in Scotland, in Dundee and Edinburgh, and our focus is very much upstream space software, and we have built a world-leading set of products and services around that over the years that we've been going since 2011, and we've focused especially on flight mission control and simulation software, and we're selling our products to customers across the world. There are currently 24 spacecraft flying our flight software, and many of those are using our ground software, our mission control software as well. We sell products for customers to use, and I'll be showing you those in a moment. And we also use those products ourselves in-house. And there are currently 8 missions in development already for launch that we have been working on, and our customers have many more. And we are also heavily involved in agency work along with ESA on R&D activities and various bits of international collaboration, especially on standardization bodies. So the whole context for all of this is really about the role of space software in the system. This is our starting point for everything that we do. And if you think about what space software needs to do, it's really responsible for functionally integrating the mission and delivering the overall service, the thing that you have put together your space segment to do. And the software that's involved here exists across flight and ground, and it has to all act together to create a single operable system. And so we need this to act together to give customers faster access to data, we need to improve satellite tasking, we need to make efficient use of resources, and overall we really need to reduce the total cost of ownership. And part of that is to allow the users of software to be independent of the hardware that they are using. That allows them to make cost decisions on one of the most expensive elements of the system. So the software needs to come together and deliver this service, and all of the elements need to work together, both across the complete system, so across flight and ground, but also across the complete life cycle from early development through to ongoing operations. And in most nanosatellite, particularly systems, or LEO systems especially, the operations phase and development phase are ongoing. There will be constant replenishment of the satellites on orbit, and there will be software upgrades. And the system is basically subject to constant change, which is an interesting characteristic of current space systems. To address this from a software point of view, what we really need is the ability to grab off-the-shelf software and apply it to our missions. And that gives us many advantages in terms of getting access to proven software and being able to reuse and leverage all of the heritage from proven software. But the challenge then is, how can that be adapted to meet the specific needs of individual missions and be adapted to the hardware systems that we have for a specific mission scenario? What we have built is technology that is specifically aimed at addressing this problem, this bespoke off-the-shelf versus adaptation problem. And we've built a technology which we've then evolved into currently 2 main products, and that's our flight or onboard software product and the operations software product. And both of those are intended to allow for rapid software development, be adaptable to mission needs, actually preserve the software, the heritage that's in the software, and have a strong focus on efficient operations and helping to reduce the total cost of ownership of space systems. So the software is there to scale to your needs and to allow decoupling between what you achieve from the system and the hardware that you're using, including perhaps the vendor of the spacecraft that's being used, which avoids vendor lock-in. So the core technology is called Generation One, and we apply it to flight software through our flight software development kit, and we apply it to operations through our mission control software. And the technology is based on three aspects. It is model-based, which means that it has a machine interpretable understanding, a model that captures the overall software at an architectural and functional level. So you could say that the tools that we're working with here, our flight software development kit and mission control software, have some kind of understanding of the functionality in the system, which is from this model. The software is built in a very modular way using very tightly structured modules, which we call software components. And we have a well-defined way of defining those that also intersects with the model-based nature of the system. Those components interact with each other through what we call services, and those are also tightly defined as part of the overall model. So this Generation One technology was not something that we just kind of sat in a darkened room with and emerged with this perfect solution. In fact, the opposite is something that has evolved gradually over time, and it's been iterated and improved upon as we have gained a greater and greater understanding of the needs of different missions out there. And every time we come up with a new potential feature with it, we tend to try it on a mission of our own before we go out and push it into the products to allow other customers to get access to it. And that makes sure that the features do what we want, and also that they're grounded in real mission needs. So I'm going to start by telling you a little bit about the mission control software, which is the operations software. So the Generation One MCS is aimed at allowing customers to operate missions efficiently. It's one of the main focuses of it, and thinking back to what I was saying about how current missions tend to exhibit a great deal of change over their life cycle. One of our core focuses is permitting rapid integration and configuration. So this uses our model-based approach. So it pulls in a model of the overall system at a functional level, and it rapidly configures the system. It covers all the key operational needs. It supports automation and extension through various APIs. It's being used on a wide range of missions at the moment and is scalable from single spacecraft up to constellations and clusters and multi-mission operations. So this model is at the heart of everything, and it provides a functional breakdown of the system, and it can display that in terms of a hierarchy, and we will show that in a moment when I show you around the mission control software. And all of the functions within the system are captured as well-defined services, and those services are what the MCS uses in terms of to operate the system. And these services are quite a high level to be working with, and it's much higher level than alternative operation software systems tend to work. So alternative operation software systems tend to work at the packet level, and then there is a great deal of work that needs to be done in the process of configuring those to turn that packet level into something which can be used by operators or by automation to provide an operable mission. And so in our case, we have focused on using our model-based approach to make the whole thing a lot more rapid to configure and a lot more operable. And that's unique to the technology that we build. But beyond that, the MCS has all the kinds of features that you would hope for and expect in operation software. So it provides you with monitoring and control facilities. It gives you telemetry visualization and archiving. It gives you monitoring with alarms and condition notification. You can use the MCS for automated pass management, and some of that can be achieved through scripting and scheduling. And so there's an extensive scripting API that is available. So what I'm going to show you just now is use of the mission control software with a simulated spacecraft that's running in the program Kerbal Space Program, which you may be familiar with. And so we're using KSP essentially as a simulation environment. And the satellite in KSP is sort of like a CubeSat, and it has some basic avionics. Particularly, it has a power system, which is modeled, and an attitude control system. It also has an Earth imaging camera payload. And we have modified Kerbal Space Program to allow us to execute our flight software, which was built using the flight software development kit, which I'll show you shortly. And then we can communicate with that in the same way as we would communicate with true flight software. The only difference is that rather than using a radio, we are using a space link over TCP/IP. So what I'm going to do is switch what I'm sharing just now to share the the screen I have here. Sorry, just a moment. And where have we gone? There we go. Right. So we have in the top left here, we have the mission control software running, and over on the right, we have here the simulation that is being run in Kerbal Space Program. So over on the left, we have the very far left, we have the space system model. So this is the model loaded in with all the different aspects of the system being shown here in this hierarchical tree. And as we browse through this tree, we can find information about different parts of the system, and it's coming up in this panel down here. And so all this information, including all this documentation, which is aimed at operators, is being loaded from the back-end model. So over here, we are monitoring the onboard battery voltage. And so we can see a previous time the satellite was in eclipse. And over here, we've actually got a view of the body rates over the last long period of time, which is why it all looks so squiggly. So I should say that, as you can see from up here, the satellite is in demo mode. And this is a mode that we've incorporated into the flight software purely to allow the satellite to generate some more interesting telemetry. So it shifts into a randomly selected ADCS mode, attitude control mode, periodically, just to make sure that we get some slightly more interesting telemetry for us to show you. So you can see this telemetry coming down here is live, and these two graph windows are being updated live. So the one thing I should also say is that for the sake of this demo, we have constant contact with the satellite, which obviously is not terribly realistic, but it does make things a bit easier to show you what's going on. In the middle here, we have a view of some files in the onboard file system on the satellite. And here, obviously, we have a map view showing where the satellite is at the moment. So each of these parts in the display here can be pulled out from this, this view on the left. So for example, I can pull out a window from over on the left, and I can actually dock it into this display, and I can use that to work with the satellite. Once I've built up a layout, like a dashboard, I can save that, and then I can switch between them. So I can switch to an alternative layout, which I've prepared specifically to do some imaging operations. So what I'm going to do, you can see that we're actually in eclipse just now, which makes life a bit exciting. So I'm just going to put the satellite into standby mode. And then I'm going to pick a location to take an image. I'm just going to select a latitude and longitude from the map, and I'll send those up to the satellite. So I'm going to command the satellite with the latitude and longitude. And then I will tell the satellite to take an image, and this is an onboard automatic image capture mode. We can see the satellite goes into capture mode, and then it will orient itself according to the latitude and longitude that we selected. I'm kind of hoping that this is sufficiently on the horizon that we might actually get an interesting image, but I think I might not have gone quite far enough. So what I might do is just take, see if I can take one more. And so I'm just going to take one off to the even more to the horizon, see if we can get an illuminated horizon. So we'll let the satellite take an image, and then let's see what there is in the onboard file system. So we have a set of images in here, and the latest image is this image 212, so we can downlink that image. So that image has come down from the satellite, and Yeah, lo and behold, it's black. Well done, me. But what I can also do is bring down some images that I took earlier that were when the satellite was in an illuminated environment. It was in sunlight. So I can bring down one of those images and we can have a look at that. So the image that the satellite has captured in that case that we captured earlier looks like that. So that takes you through an image capture, which was just a basic commanding of the satellite and the ability to work with files on board the satellite and work with telemetry. So what should be noted in all of this is that at no point did I have to think about or worry about the exact packets that were going to and from the satellite. I can work with the satellite at quite a high level. And that's not because I have specified to the system very detailed operations procedures or something like that. It is purely because I have pulled in this model which defines all of that for me. So I can take us over back to our slides, and I'll just wrap up what we've been saying about the mission control software. So there is many things that I haven't shown you. There's just a quick tour of the user interface for the mission control software, and so there is extensive built-in support for ground-side scheduling and to enable operations to be automated. There is built-in scripting and a command line in there that's based on the Groovy language. There's also scripting capabilities based around Python, which actually has a really powerful interface. The services that are used to access everything within the system are basically fully exposed to Python. And so that means that Python can access everything that the mission control software front end can access. So the MCS itself is it's a rich client software platform, as you could see, and that's for installation at the site that you want it to be used. The entry-level version, what we call the Foundation Edition, is a monolithic application, but the more powerful editions, the Standard Edition and our forthcoming Professional Edition, are client-server. So it's a back-end server with potentially multiple clients for multiple users, and it supports multi-spacecraft and multi-mission environments. We can integrate it with third-party data analysis tools, particularly web-based data analysis tools, including live update of those. That includes things like Grafana. And there's also a developer edition available, which is just the back end, and that's intended for integration into third-party systems. And I should say that the MCS is under very active development at the moment, and we are adding a huge amount of features to it on a regular basis. And that's particularly being steered by all the missions that we're involved in supporting operations for. The MCS obviously integrates completely with our flight software, and what I'm going to show you next is the flight software development kit and the way that that will actually automatically generate one of these models that can be pulled into the mission control software. The MCS can, in some situations, also be adapted to any flight software, and it depends on the flight software as to the best way to achieve that. So I'll move on now to talk to you about the flight software development kit. So this is a kit that is intended to help people build flight software and to get that ready for use sooner, to allow people to leverage the existing technology that we've built and to get access to the heritage that we've built and all of the missions that the software has been flown on, but still be able to tailor it very specifically for your mission. And there's a huge amount of flexibility in doing this. It also is highly portable, and that is not just for your mission, but also within your mission, within the development process. You can prototype on one system, you can then move it to another. So for example, prototyping on readily available single board computers like Raspberry Pis, and then being able to move that over to real flight hardware as your development process goes on. So the flight software starts from the point of view that most spacecraft need to perform very similar tasks in terms of data acquisition and monitoring and logging and fault management, so fault detection, isolation and recovery, being able to communicate with ground, telemetry and telecommanding, and to perform scheduled and automated actions. And yet, when you look at any mission in detail beyond those things, every mission ends up being different. And there is no way that a single piece of pre-built flight software could be used on a particularly broad range of missions, because payloads are always different. The way that telemetry needs to be handled for a specific mission is different. Because of the larger mission architecture, different communications protocols may need to be used. And that mission architecture may also demand a distinct concept of operations. You're going to need to operate your system in a way that you have defined and that's suitable for the service that you're trying to deliver. And so there needs to be a way of tailoring the software to meet your mission requirements, whilst also preserving all of the heritage of off-the-shelf software. So that's where we take an approach that is based on these software components that I mentioned earlier. And this is pretty much like starting with a big bag of Lego bricks, and all of these individual software components, these individual Lego bricks, have been flight proven, and you can then build software using these blocks. And it's this level of modularity that allows you to tailor your software for the mission by choosing which components you use, how many of each type you use, because you can instantiate some of them multiple times. You can configure the components differently, you can connect them together differently, and obviously the tooling and everything supports custom components for your mission. You can create and manage your own components, and that is especially important because it allows our customers to use the system to manage their own software reuse. So it's not just about reusing what we provide, it's also about you creating your own reusable blocks, which you can reuse from mission to mission across time. So as you go through the development process, it builds a model of the software, and that can be used to generate documentation, it's used to generate code, as I'll show you in a moment, and it also, that model then goes into the mission control software. And overall, this has been proven to reduce development time, cost, and risk, and provide software that's available much earlier in the development lifecycle. So this level of modularity is only possible by having quite fine-grained components. Some components are actually really quite small, and the only way that that can be made possible and easy to use is by supporting all of the code there with a range of tools, and that is a core part of what the FSDK is. So it's a complete toolkit for building flight software that's installed on your development PC, and it provides a set of development tools for giving you this workflow that allows you to access the extensive library of components that we provide, and that library covers all of the major flight software functions and needs. There's also graphical test tools to allow you to work with your software during development, and that tool, the main graphical tool there, is actually a cut down version of the mission control software with some tweaks to make it especially aimed at rapid iteration of your software during development. There's documentation with the FSDK, as well as tutorials to assist you with how to use it and to provide best practice guidance. So obviously the flight software and the tooling integrates with other products, especially including the mission control software. So this might be a little bit busy. Apologies if it's tricky to read. This is just some examples of the kinds of software components that sit within the flight software development kit. So the easiest place to start is talking about subsystem components. This is where the software components represent pieces of hardware. So they're easy to understand because they're really tangible. So things like an electronic power system or a battery and so on. And the libraries contain an extensive range of these, covering a lot of the subsystems which are used on CubeSats, but also an increasing number that are used on small satellites and larger form factor spacecraft. Then the the data handling system that you need will be built out of components as well. So that's components for things like sampling of data, data pools, which are like caches, aggregation, logging, monitoring, and so on. The communication stack is also built out of components, and this provides a huge amount of flexibility for the communications protocols that you use and how those are interfaced to things like onboard radios, modems, and that kind of thing. There is support for a wide range of automation concepts, including time-based scheduling, event-based automation, and onboard scripting. And there is obviously support for mission-specific components, which are typically used for orchestration. And we provide a number of examples to get started with those. And some of the examples we provide are a complete flight software for particular platforms, and your target platform would likely be different, but it does provide you with a complete example to look through to see what is used in practice. So the process for creating flight software is to specify the interface to the component. Now, I should say that we're going to get a bit technical here, so bear with me. If you are not a programmer, then perhaps just try and get the gist of what I'm saying. And yeah, I won't be showing bits of code for very long, so you can hopefully just bear with us through those moments, and I'll show you what those mean in practice as we go through. So the interface to components is defined in a short file in a format called XML. You may or may not be familiar with that. And then once you have defined a component type, you can then implement that, and the tools will help you do that. And that creates a reusable software component. You could then actually describe how the components, the instances of those component types, should be put together to make your flight software. And that's what we call a deployment. And that's also described in a short XML file. Then the tooling really kicks in, and that generates all of the code that's necessary to put these things together. And we use code generation because it helps keep the amount of software that's being flown on your spacecraft as minimal as possible. So it keeps it really efficient. And that means that you're not flying lots and lots of unnecessary generic code that can cope with any situation whatsoever, even if it's one you're not using. The code generation tooling is either based on the Eclipse IDE or there's a command line version of it that can be obviously used from the command line or integrated into your development flow and into your DevOps. So things like continuous integration and things like that are then supported. So all of the code, including the generated code, is standard C, which follows a rigorous coding standard that we have developed in-house and follows an automotive industry standard called MISRA C, which is for safety critical C code. The generated code, just like all of the code that's in the libraries, is highly readable and fully commented. So the overall development flow starts with defining your component type. You can then use the tooling to generate some skeleton C code, which you can then implement your component in. You can then define what we call a deployment. That's a flight software instance. And then you can generate code from that, configure it, and build a binary to go onto your target. At the same time, you can generate documentation in the form of HTML pages, and that's a very high level of documentation aimed at an operator, for example. And generate what we call a spacecraft database, which is a snapshot of the model, which then goes across to the mission control software. For these component types can be collected together into libraries, and those libraries are a really fantastic way to collect together the things that you want to be able to reuse, for example, to build up a set of component types that you want to reuse in-house. So you can use the tooling to generate library documentation for any of those libraries. And that means that a library is a really good unit of exchange to pass between members of your development team. when you're generating the initial component types, you can also get the tooling to generate a skeleton unit test, and we've integrated a unit testing framework into the flight software development kit. So I'm going to show you the flight software in action. I'll quickly show you some flight software running with the cut down version of the mission control software, which is called TMTC Lab. And then let's walk through a development process. And I'll show you the whole process of creating a component type, adding it to a deployment, firing that deployment up and talking to it. And then we'll talk about what's happening in that scenario, and also how easy that has made the development process. So I'm just going to switch what I am sharing now to be a virtual machine that I have an installation of the flight software development kit in here. And this means that I can have everything all pre-configured. So this may look a little bit similar to the mission control software, but without the graphs and things. Down the left-hand side here, we have the tree of components, just like in the mission control software, and we can talk to our flight software. So here I can query a parameter value, and I can set that parameter value as well, for example. And up here, we've actually got a log of all of the low-level packets going to and from our system. So that flight software is running here in this console. So what I'm just going to do is kill that flight software and just get rid of TMTC Lab. And here is the Eclipse environment, which I'm going to use to edit some code. So each of these projects down here are either component libraries, which are marked with a little blue L, or they are deployments, which is marked with a red D, although both of those things might be a bit small for you to see, so apologies. This component library here is the application component library, and it already contains a wide range of components. And what I'm going to do just now is add a component to it. So I'm going to just get the component, the Eclipse environment, sorry, to create a new component type. And I think we're going to call that component type demo. And that is going to generate us a single component type.xml file. And we will find that in the demo directory. So here it is. This is the one that we have just generated. Going to give that a moment to load up. So at the moment, it's a fairly empty XML file. So apologies if code is not your bag, and double apologies for XML, because I'm not sure that XML is anybody's bag. But it does provide a kind of least worst solution for being able to describe our component types. So this provides a skeleton showing you all of the things that we can put in here. And what we're going to do is we're going to add two things to this. We're going to add some what we call actions, which are much like commands. So there is a section here for adding actions. And what I'm going to do is add a simple action, which I'm just going to call say hello. And I'm going to give it just a quick description to say what it's about. And this one is just the description of this, which is effectively its documentation. Say hello to the folks at SmallSat 2021. So there we go. So we're going to do that. And then we use on components, we use these things called parameters. And these are, as I'm sure you can imagine, effectively telemetry parameters, but they can also be used for configuration. So they can be read-write. So I'm going to add a parameter in there, and I'm going to call that example param, and we're going to add another little description there, and that description is just to say that this is an example, and we're going to make this a number. So we're just going to make it a value. So this is an unsigned value, and it's just going to be 32 bits in size. So there we go. So what we've done here is we've created we've defined, a reusable software component. We've defined the interface to it, and it's going to have a command, what we call an action, which is called say hello, and it's got a parameter on it. So this is quite a high level interface, and this is the interface that the operators and the automation and things like that will also be able to see. So to actually implement this thing, I'm going to generate some skeleton code for it. And this is going to be a portable platform independent component. And so it could be used on any platform. I'm going to get the tooling to help me out with some simple things. And here we're going to generate some files. So the interface to all of this is all in C, and the interface to it is defined by, in this case, 5 C functions. 2 of these functions are to do with the life cycle, setting up and breaking down effectively the component. And then there's 3 more functions. One of them is a handler for the command, which is say hello, the action, and then 2 of them for accessing the parameter, for getting and setting the parameter. So all I need to do with this to make it do something a bit more interesting is that I am going to implement this currently unimplemented command handler, this action handler. So I'm going to use a bit of code which uses our built-in logging mechanism. This is going to say, hello, small sat. And there we go, that's that. And it's now going to return success to say that it has been correctly executed. I've implemented it. So that's it. That is our new component. Our brand new component type is now in a library. We've implemented it. So now we're going to use it. And that is going to be used in our Linux deployment, which we were using, which I was just showing you a moment ago. So this XML file defines all of the things inside this deployment, and it pulls in all of the types that we're going to use. And we've just created a new type, which is called demo. So I'm going to add that. All the things in here at the moment are parts of the data handling system, the communication stack, all sorts of things are in here just now, even for this relatively simple deployment. And the section down here actually sets up all of these components. And what I'm going to do is bung a new one on the end. And because ours is quite a simple component, there's not a lot to say, really. So we say that we want a new component. I'm going to call it my demo. And it is of type demo. And that's it. So what I can do from that is generate the code that goes along with that. So we're going to generate our deployment. And this will, at the same time, regenerate the documentation for the deployment and the spacecraft database, this snapshot of the model which gets pulled in to the ground software. So I'm going to actually build this. I'm going to do a specific build which stops it from building unit tests because there are quite a lot of unit tests in the libraries, and we would be here all year if it was going to build all of those as well. In the meantime, I am going to kick off, I'm going to fire up TMTC Lab again whilst it's building. And TMTC Lab, when it launches, will pull in this new, the new spacecraft database, this new model snapshot, which will include the new component which we have just created. So I did warn you that there was going to be a bit of code, so hopefully that wasn't too difficult. And it's being built in the background. You can see there that it's rebuilding the software image, and it's onto rebuilding the deployment, having built our new component type. So if we have a look in the tree here on the left-hand side, here is our demo component. And if I launch the software, so that's now running, we can actually interact with our component as well. I'll pull up the debug console here. We can We can send a telecommand to the spacecraft. We can send a high-level command, this say hello. So we can execute that, and you can see that the necessary packets go back and forth. There is a telecommand packet, there is an acknowledgement from that, and here's a log message, and you can see that the hello smallsat message has come out down there. And here's our example parameter, and we can set the value of this parameter. Like that, and that also turns it into telecommands and so on, and we can get the value of that parameter back again. And so you can see that our new software component has a completely functional parameter. So what's important to note here is that in terms of the code that we're writing, we are focusing as a developer on the functional code, the thing that actually adds value to what you're doing. And we didn't at any point have to worry about handling packets, about encoding them, decoding them, and so on. So the focus really is on getting the most out of your system from the development process onwards. And when combined with the MCS, it really is about getting the most out of your overall space system. So I've taken you through the demo and showed you how a component type XML is used, and used the tooling to generate code stubs and so on. And then we ran our new deployment at the end. So all of the components are abstracted from the underlying platform. The application components, like the one that we made, are completely portable across platforms. And the vast majority of the components in the libraries are portable. We use very simple operating system abstraction, and that allows us to work with a wide range of operating systems, including real-time operating systems like RTEMS and FreeRTOS. We can also work with any POSIX-based system, that includes Linux, obviously, and we can work in a bare metal environment using a built-in cooperative scheduler. The way that our abstractions are structured is specifically to allow tool integration for proof of real-time properties of a system, such as schedulability. The platform abstraction allows us to work with a large number of platforms, and that includes a wide range of Linux-based systems and ARM platforms, Leon-based systems, that's Leon Spark-based systems, MSP430s and more. And we support a wide range of off-the-shelf onboard computers. All of the abstraction of devices is based on components. So this is platform-specific components that are suited and built in the libraries for specific platforms. And so that's for particular interfaces like CAN interfaces or SpaceWire or I2C, SPI, and so on. And the way that we structure those is, and the modularity actually draws on some CCSDS standards for interfacing. We support a wide range of protocol stacks, including many CCSDS and ECSS protocols. So the overall architecture builds on a platform support package, some of which may be supplied by the vendor for the onboard computer. There is a slim framework that sits on top. This is a very small amount of the overall code. The vast majority of the functionality of the system is structured in these components up here, platform-specific system components and portable application components. So the component library covers all of your basic needs for flight software. There's automation components in there. There is built-in support for building distributed systems. So that's building systems of multiple computers. And that allows a multi-computer system to be operated from the ground as if it was a single system, and for the different parts of the system to talk to each other. So that can be used for creating payload computers, for example, or for creating more multi-purpose onboard compute facilities. All of this separation of concerns, this way that we split out the functional and non-functional code. So when we were writing a component, we're really focusing on the functional code, and that is there to facilitate reuse and portability. The framework supports the persistence of component configuration. So that means when you reconfigure, for example, your telemetry in flight, the component can ask the framework to persist that across reboots. There's a huge amount more in the system which I haven't covered, and which I'd be happy to answer questions about or come back to you at another time. I showed you TMTC Lab. It's also possible to hook up Python to that, particularly for automated test. And the FSDK is also under very active development, and we're working on a wide range of areas, including tool improvements, and we're always adding components to the library, additional platforms and operating systems. So our licensing structure for all of this is we use a common licensing structure across the different products. The main editions we work with available on the MCS are the Foundation Standard and Professional editions, which I mentioned previously. On the Flight Software Development Kit, we currently have a single license which effectively maps to a standard edition license, and we may be able to arrange other licenses, such as a perpetual license, if that's the right thing for your project. We can support all of this with training, mentoring, bespoke developments, and as I mentioned earlier, we also use this in-house to develop full flight software and tailored operations software for specific missions. We have also recently announced our Bright Start academic program, which gives you access to both the mission control software and the flight software development kit free of charge for classroom use for any academic institution. And we're really excited to continue our support for universities and hopefully provide it to a much larger range of universities, particularly to support learning and skills development. In order to use it within an academic environment for flight, there is a license charge, but it is massively discounted from the other prices to hopefully put it within easy reach of most university flight projects. So if you have questions or comments or suggestions, then please do bung them into the Q&A just now. I'd be happy to answer questions. Also, if you would like to follow up with us, perhaps with questions, or you would like a demo session, or you would like to follow up with us for a 30-day trial license, then please do get in touch.